Hi chemists, fourth video in our polymer chain. Oh, terrible. This next one, we're still talking about condensation polymerization. It's the second example in our syllabus point. We talked about polyesters. We need to talk about nylon. And nylon is a type of polymer that is called a polyamide. And they're polyamides because they have amide functional groups in them. So we've already encountered amides and polyamides in the last chapter where we discussed amino acids and their ability to form amide links between them. Okay, so one of the most common biological polyamide are proteins. They form those peptide links, I believe they're called by biologists. One of the most important synthetic polyamides is nylon, and that's the one given in the syllabus point that we're talking about. So, like the polyester, they can either be made by one monomer or as a copolymer. Okay? So, amides are made by an amine and a carboxylic acid. So if we're making them from a monomer, it must be made from a single molecule that has a carboxylic acid on one group, on one end, and an amine on the other. Look at this molecule. So it's called, this molecule, an amino acid. Okay? And you get a condensation reaction where you break that bond there, and you break the carbonyl CO, and you end up with H2O left over. So in this monomer here, I've got 2-aminoethanoic acid is our name for it. The biological name is glycine, ACTG, the G in there. So this is the amino acid glycine, but as chemists we know it as 2-aminoethanoic acid. It's a monomer that's going to form a polyamide. It's going to form poly, in brackets, 2-aminoethanoic acid. Okay, so each link there, those three links, have given us the three waters left over. 4 molecules, 3 links to join them, 3 waters dropping out. And so what we end up with is, look at these functional groups in the chain. The carbonyl next to a nitrogen is called an amide, therefore polyamide. Okay? Ongoing amides in the chain, polyamide. So if you're making a polyamide from a single monomer, you make it from an amino acid because it has a carboxylic acid and an amide on one end. And so you get one monomer going to a polymer. Okay. Nylon. Let's talk about this one. It's the general name for synthetic polyamides. Okay. Single amino acid, or as a copolymer between a diamine and a dicarboxylic acid. We need an amine and a carboxylic acid, so we need 2 molecules, one that has an amine on both ends and one that has a carboxylic acid on both ends. So nylon, okay, the various types of nylons. I'm going to talk about one that's called nylon 6 first, okay. Nylon 6, it only has the one number after it, is made of one monomer. And it's made of one monomer because it has, I've just rubbed it out, one number after it. Is made up of 6-aminohexanoic acid. And I know that because there's only one number, so it must be made from one monomer. And because it's a nylon, it must be a carboxylic acid on one end and an amine on the other end. Okay, and there's a 6 in there because there's 1, 2, 3, 4, 5, 6 carbons long. So it's 6-aminohexanoic acid will polymerize and form nylon 6. So it's a condensation reaction where you get your carbonyl carbon breaking with the next oxygen and one of the NH bonds. Condensation coming out, and you get a polyamide, an amide group, and it has It has, look at this, it has CH2 5 times in between, and then the 6th carbon is the carbonyl carbon, okay? So therefore the hexanoic acid kind of, they've summarized as 5 CH2s in between, and the 6th carbon is the carbonyl carbon. So you get an ongoing chain of NH, so a single hydrogen coming off it, and then your 5 CH2s, and then your carbonyl carbon repeated. That is nylon 6. There is only one number after the nylon, so it must be from a single monomer, so it's not a copolymer nylon. Let's look at nylon 6,6, which, because there's two numbers, it's a copolymer nylon. It's made from monomers 6 carbons long. So we must have a diamine and a dioic acid, and so they're 6 carbons long. So I have 1,6-diaminohexane, or 2 amines with the hexane backbone on in the between. And we also have hexandioic acid, or I have the hexane backbone, but on the ends I have 2 carboxylic acids, hexandioic acid. So they polymerize as a copolymer. You get the NH bond and the carbonyl CO bond breaking, forming water in between, okay? And so you get this one here. So there's your amide groups, okay? In between the nitrogens, you've got your 6, your CH2 6, so you know you started off with the 6 carbons, and in here you've got your 4 and then the 2 the 2 carbonyl ones. So you've also started with a monomer 6. So therefore the nylon 6,6, there's 2 numbers, so it's a copolymer. The first one is the diamine, and the second one is the dioic acid. So nylon 6,6 is made from 1,6-diaminohexane and hexandioic acid. So nylon X in general is made up of a single amino acid that has X carbons long. Nylon YZ is a copolymer diamine. So it's a single copolymer where the diamine is Y carbons long and the dicarboxylic acid is Z carbons long. The longer the chain, the more CH2s in between, the lower the melting point and the less it absorbs water. Okay, let's briefly go over condensation in sugars because it has been in past HSCs. It's not directly addressed in the syllabus point though, but so we can quickly go through it. We've talked about it last chapter when we talked about fermentation and how sugars, there's different types of sugars. You can have monosaccharides which have single rings in them, or you can have disaccharides where they form a condensation reaction between 2 and they have 2 links, or you can have a polysaccharide like cellulose where it's ongoing rings all joined up, okay? Oh, that's what I just talked about here. Okay, so condensation in sugars. So when sugar rings join up, or those saccharides join up, you get condensation reactions. So a polysaccharide is a polymer of these rings, and it's a condensation H2O dropping out with every link. Okay, so in general, remember, the starches and cellulose have these ongoing rings with joins, and each join you're dropping out a H2O. Okay, so further condensation leads to a polymer of sugars, are polysaccharides. And the three most important polysaccharides are starch and cellulose and glycogen. So keep it as starch and cellulose. They're all polymers of glucose, but they differ in how they're branching and links and stuff. Okay, let's look at some past paper examples just in case. It's not on the syllabus point though. So glucose is a monomer that can form naturally occurring polymers. The approximate weight, oh, I need a calculator for this one and I don't have one. The approximate atomic weights for the elements, oh look, we know that anyway, as shown in the table. Using data from the table, what will be the molecular weight of a polymer made of 5 glucose monomers? Okay, there's a trick here. They've given you the formula of the monomer, okay? What you need to recognize that it's a condensation reaction, and each join is losing a H2O. So we're going to have 5 of those of C6's H12O6 coming together and polymerizing, and it's a condensation polymerization. And because it's condensation, it's going to lose a water for every link. There's 5 molecules, there's going to be 4 links. So it's going to lose 4 H2Os. Okay? So the product is going to be some chain. I'm not even going to worry about the structure, but it's going to be 5 times that minus 4 waters. So it's going to have how many carbons? It's going to have 6 times 5, which is 30. Okay. And it's going to have, for hydrogen, it's going to have 12 times 5 is 60, but it's going to lose the 8 from 4 waters. So 60 minus 8 is 52. Okay, and it's going to have 6 times 5, which is 30, minus the 4 from the waters. 30 minus 4 is 26, O26. So, we've got the formula for our polymer made from those 5 monomers. Now we would need to work out the atomic mass. So it's going to be 30 times 12 plus 52 plus 26 times 16. I haven't got a calculator on me. Let's see how I go. 30 times 12 is 120 for each 10, so it's 360. And it's going to be 52 times 1, so 52. 26 times 16. Oh, how good am I going to be at that? 260 is going to be 10 times it, plus 130, so that's 390 for 15, plus another 16, 390. Oh, I need a calculator. 20. Oh, this is really boring. And you're probably yelling out the answer. Okay, 15 times. So 260 is going to be 10 times, and then we've got another 5 times. So that's going to be 130, and we've got another 1, so that's going to be 26. So it's going to be 6, 11, 3, 4, 416 I get. Plus 416. Okay, let's add these together. Terrible working. 52, 4, 16. So that's going to be 8. 6 and 5 is 11, 12. 7, 8. 828. Look at that. We get B. Okay. What type of reaction describes the polymerization of glucose into cellulose? It's not an addition. It's not a hydrolysis. It's a condensation. We've just been talking about it. Water is released during a polymerization reaction. What monomer is likely to have been involved? Okay, if water is released, it must be a condensation reaction. Condensation polymerization. Ethene is addition monomer. Glucose, is a condensation. Styrene is an addition, and vinyl chloride is an addition. So glucose is our answer there. Okay, let's just talk about this one. It's an 8 marker. Compare the process of polymerization of ethene or ethylene and glucose. So you're going to have to go over ethene is an addition, glucose is a condensation. So you need to compare addition to condensation. Involve relevant chemical equations in your answer. Okay, glucose, don't remember the overall structure, but just talk about rings joining up. Explain the relationship between the structure and properties of 3 different polymers from ethylene and glucose. Okay, just talk about cellulose as one of the rings, as the chain of rings, and compare that, and talk about low density polyethylene and high density polyethylene. They're the 3 different polymers. Talk about the properties, how they differ, and talk about their different uses. What's cellulose used for? Structure of trees. Okay, I think we're going to call it quits there, and we're going to use a new video to talk about these. So that's just a short one. Thanks for your time.